Hello, how are you doing? Okay, so today we're gonna do the lab that we didn't get to do last week. So make sure you check out the lab for Unit 8. And I will go into screen share shortly. So go ahead and download the lab if you haven't done that. Let me get my document up here. So today we are going to do multiplication and division in assembly. And I want to make sure I have my editor open. Okay. So let's screen share real quick. Okay, so let's check out the lab that we didn't get to do last week that was pushed from Unit 7. You're going to do multiplication and division. So in this week, we are going to write subroutine, and then we're going to use subroutine call, which is going to be in JSR. So for this week, we have a problem statement. This is from the original lab book. We are going to revisit the multiplication problem in the following week, where we're going to rewrite the program to make it faster. So, not next week, but after spring break, I mean. Okay, so no school next week. So the problem statement is given to you that you have X and Y, and these are going to hold integers value. We're going to compute the product of X, Y, so we're going to multiply. And we're also going to compute the quotient of X divided by Y. So we're going to use integer division, and we're going to do modulus. So we're going to do X mod Y to get the remainder. So we have to write all of these into one program. And the input integers are going to be X and Y. We're not going to have the user input, but we are going to test the program by setting the value at location. X is going to be at 3100 and Y is going to be at hex 3101. So those are given to you. And the output, we are going to put the product of X, Y, and quotient XY and mod X mod Y, the result for that. We're going to store it in the subsequent location 3102, 3103, 3104. Okay. Now, if X, Y inputs are invalid for X divided by Y or X mod Y, we have to look at the section 5.2.5. So this comes from their lab manual, lab 5, and on the page. So I clipped those and I put it in your assignment for you. And so we are going to use the input to be able to validate. So for the X divided by Y and X mod Y, we are going to go to location 3103 and 3104. So in this program, we're required to implement subroutine, and subroutine is equivalent to your functions in C++. You might be familiar with routines or subroutines from other languages. So subroutines are functions, and we are going to use the definition of our functions, and we're going to do function call, very similar to your other languages. So it's a form of group of code that's intended to be used or be reused multiple times. So that's the whole purpose in writing a function, is that you can reuse that section of your code by simply calling on the function. So when you're doing a task that's that can be reused or be redone, then you can put that into a function, and then you can simply call a function. Subroutines need to perform logical tasks by offering parameters that's passed into them. And in programming language, we know that we can pass variables, we can pass. So the parameters that you're going to use, similarly to C, C++, right? We are going to think about how we're going to implement that in assembly. Now we want to return from the functions, and that's the whole point in writing a function. You know, in the case of C, C++, when you are not returning from a function, you would use a void. But when you're returning from a function, you would use a typed function. So that will be int, long, etc. So in this class, when we're writing subroutine, we want to return from our subroutine. And in this lab, we're not going to do the RET yet. We're just going to call the subroutine based on what we're calculating, and we want to be able to store the value and load the values accordingly. So when we're looking at the example in the listing, when it implements f of n is equal to 2 times n plus 3, and when you look at this function, you can see that we need to operate a multiplication here and an addition, right? So for the integer n is located at hex 3120. So the result of the function is stored in a subsequent location, which is going to be at 3121. And so when you are writing your project program, think about how you're going to set up your memory locations. So normally you would go to the subsequent or the next one on that list. So that way, when you check your program, it's simply easier. Okay. Now for the register 0, this is used to pass the parameter to n to the subroutine. So it passed the parameter n to the subroutine, and register 1 is used to pass the return value of f of n. So you would see that instead of using a variable, which is ultimately an identifier for a location in memory, we're going to use a temporary memory location, which is your register files. And registers can be used as parameters in your function. So think about how we will be able to implement the registers there. Now, execution is transferred to the subroutine using JSR. So JSR stands for jump to subroutine instruction. And what this does is it saves the return address as an address of the instruction follows JSR in the register 7. So it specifically used register 7 to store to save the address of the return, okay? And as it terminates the execution via the RET statement or return from the subroutine. So in C++ and C, when you're doing return, right, the compiler handle this. So we have to think about how we're going to be able to bring the address to the register so it would associate that address to the return value that we're returning from our functions, okay? And so we would assign the return value in register 7 to the program counter, so that way it would know where to go to retrieve the return value from after it operates, after our function is called, okay? So in this one, and I will expect you to write subroutines and do JSR for your subroutine. That's basically your function call. And you can see how we're going to be able to set that up in this lab and all the subsequent labs. That's going to be one of the grading components. So when you come back from spring break, we'll talk a little bit more about your projects, about, you know, the requirement, the criteria, what I'm going to be, what kind of rubric I'm going to be using to grade you on your project. So, you know, so this is the beginning on how you would be able to implement your subroutine in the program. So there will be two subroutines that's going to be used in this particular program. We have one that's going to call mult, and that's for multiplication. We're going to multiply the values in x and y. And we're going to do a second subroutine that's going to be div, stands for division, and mod. Okay, so we're going to handle those two in the division. Now, from the listing from the lab manual, this is the snippet for listing 5.1. So here is a little snippet on, this is going to be the hint on how you would be able to write your program, or at least some part of it. So in the example that we saw, that we would have 2n plus 3, okay? F of n is 2n plus 3. So you are going to take the n and you're going to load it to a register, right? Because we have to treat this n somehow. And in this function, when we're looking at the function, n is going to be your input. So whatever the value we set for n, right, we want to find a result in the f of n. So we need to load the label n to register 0. And unlike C or C++, so think about how in C or C++ you will call the function in main, okay? So in assembly, you would do a jump to subroutine at the beginning. You need to call it first, and then you define it below, okay? So you would need to do a JSR, and whatever your function name or your subroutine name is, and in this case it's F, then it's going to go here to operate the function. So your function definition or your subroutine definition is going to be below the function call or the JSR. Okay. So here, after we load n, we're gonna do a JSR subroutine named F. So it's going to jump to the subroutine. So at this point, it's going to go here. Okay. And here, what they did was they fill it like up here, but you can still fill it somewhere down the line. It doesn't really matter, but I like to keep the data section separate. So that way, you can edit it and you can go there and reference it. It's a little bit better than going back and forth in their various data sections. So here we are going to store, right, register 1 to Fn. So because remember that earlier they mentioned that we need to have a register that's going to handle, right, F of n. So in this case, it's register 1. So we need to store R1 to Fn, which is going to be our result. Okay. So our result is going to be stored from register 1 to the location Fn. Then when we fill, we need to fill n at 3120. F of n is at 3121. So those are going to be the address. So when I test this program, I'm going to set the value at 3120 in my simulator. And after I run the program, I would go to F of n, which is 3121 right below that, to see the result. To see if I input n as 1, I wanted to see if 2 plus 3 is going to be 5, if 5 is going to be there, right? Okay. Now here they show you how you can define your subroutine. So here we call it F. And you want to clear out your register. So because we're using R1 for F of n, so we're going to clear out that register. So when you write your subroutine, you have to think about, okay, which register I want to start with. And we don't want to use R0 because R0 has already been used, or it might be used for some other things. So you can start with register 1. Then we are going to copy, right, from register 0 to register 1, because that's our n, right? So at this point in your mind, you have to say, okay, how do I really write it out algebraically? Or a function in general, right? I would say f of n is equal to 2n plus 3. So we have f of n, which is going to be R1. Now we need to bring in the n. and then we need to double it, and then we need to add 3 to it. So it is a sequential process that you're going through in the function definition. So step by step, you have to really piece that function and add it to the definition of your subroutine, you see? So here, why am I copying register 0? Why am I copying register 0 to register 1? Because I have to bring the n to the register that's going to store the result, right? To represent this function. So here at this point, I copy R0 to R1. Then I add it again. Why do I add it again? Because it's 2n. So when we copy it, that's only 1n. And in order to represent 2 times n, we just simply add it again to have it 2n. So here I add again itself. So you would have 2n at this point. And then now I just need to handle the plus 3. So after that, the next line is going to be adding the hex 3 to R1. And so after this, you would have f of n is equal to 2n plus 3. So no matter how complex your function would be or your equation would be, you have to really think about how you're going to go step by step in introducing your variable, right, and your constant to that function in the definition of your subroutine. Okay. I had somebody that contacted me on YouTube because I put up this class YouTube video, right? Asking to solve an equation in LC-3. And I wrote back and, I did explain the sequential process on how you would be able to implement the subroutine. So when you approach this from a lens of a student, right? And, even in development, we have to really think about how we're going to get from point A to point B. And in assembly, it's really simple. It's about how we're going to take one piece, add it, and then make that piece to represent the next part of your equation, and then move to the next part of your equation, and so on. And eventually, when you go through it and you're tracking your register, you would have the complete equation. Okay? Any question? All right, so that's a good example to follow. Now, here they give you the step on how that subroutine is set up. Okay, so in step 1, we have the PC counter. When you jump to the subroutine, it's going to take the address of the instruction in the definition of the subroutine, and it's going to increment it by 1 because it needs to read, right, what you're trying to operate there. And so when it operates your function or your subroutine, that's going to go through the IR. Your register 7 at that point is going to initialize at 0 because down the line we clear the register 7 because register 7 is going to store your return address from your function or your subroutine, so that way it would know what the value would be after the operation, after it computes that function. Okay. So in step 2, you already have your address increment there, your JSR there. So at step 2, your register 7, it's gonna copy the PC, which is the address, right, of your subroutine with an increment of 1. It's going to copy that in the register 7. And that address is important because that's the location where it's going to store the result, okay, the return value. Okay, so it copied the PC to R7 for the return instruction because the RET, right, that's going to allow us to be able to retrieve the value or see the value in the result of our return from the function. Okay, so in step 3, okay, your PC is going to be updated with the address of the definition of your subroutine, which is F. Okay, because here it's going to add the address there. And then your R7 is still going to continue to have the JSR address +1 because that's your return address. So here it tells you that it's going to copy the F address from the IR to the program counter. So execution will proceed from there, because if it doesn't know where to pick up in your program after that function, right? Because we might have 5, 6, 20 different subroutines. So it needs to pick up like after it operates that function. So it needs to go increment it to the next line. So if you have another function, or if you have, other things that you need to operate, it's going to go from there. Okay. So here it gives you a little bit of a flow on what happens in your subroutine and in the call of your function. Okay. Now, one of the things that you're going to see in this program is going to be save and restoring, and I will expect this in your project, right? I will look for it. I read all the code when I grade the project. So, I will expect that you know how to do save and store register. And this lab is a good example. So here it talks about the beginning of your subroutine. You need to save all your registers that will be destroyed, because if data gets modified in the register, right, you need a save. So let's think about that. Just like how when you're doing your homework, you think that maybe if your files get corrupted, right, sometime in between the start to the end of your homework, you want to click save. And so the process in this is we have to think about if your data is going to get modified or changed or destroyed, we need to make sure that we put it into a register, and we're going to tie that register to an address. So we can then go there and retrieve it later. Okay. Because sometimes, like if you're overloading a function, think about overloading a function in C or C++ or Java, right? The compiler handles that when you overload it, it stores the value into a certain location, and then we can update it. So if I'm looping something, or if I'm overloading a function, I can always go to that temporary location to be able to retrieve. So the whole point is to really set up a location, right, that would tie to a register, so that way we can go and get the value that we originally computed for a later use. Okay. So here it talks about before returning to the calling of the program, restore the save register. So you have to save the register and then come back and restore from it. So that means that I have to store the register to a label. And then later on in the program, I'm going to load right from that label to the register so I can use it, right? Like what I mentioned before, if you start with store, you have to load at the end. So when we save and restore, we're going to store the label to the register, so it knows that that's the location where the data is going to go, right, throughout the program. Then we are going to go back to that location at the end, and we're going to pull the data from that, so that way we can return the value. Okay, so it is very manual in the aspect that you have to think about how you would set up these locations, and you don't fill it with a permanent address. You can just fill it with a hex 0. Okay, and what that does is it's going to take a location, right, not necessarily at a specific address. It's going to be part of that program, and it's going to put the value there. And so that way we can take that value and we will return. Okay. So here in the listing 5.2, it shows you how that is done. And normally, for this class and when they teach it at the university as well, we normally use register 5 and 6 for that, because normally, 7 is used for other things and 0 is used for other things, and you want to use 1, 2, 3, and 4 for your operation in your definition of your subroutine. Okay, so you normally see programs in LC3 uses save register with 5 and 6. Can you use others? Yes, you can. But just the way that we teach this, that we dedicate 5 and 6, so that way it's easy for you to remember. Okay, so we would do save and restore register. So you start with the save register and you would restore from it. Any question with this? Okay, so let's take a look at lesson 5.3. A lot of this, you already have my code. I posted that already. So, we'll take care of the code part. That's fairly quick. But I want to explain this because in the next lab, we're going to have to do multiplication again, but with bit shift. So after this, you should know how to use save and restore and do JSR for your subroutine and write a function definition, okay, in assembly. So the structure of your program, the flow of it, you would see that at the beginning, right, we're going to load your label, okay, and then we are going to do subroutine call, which is JSR, and then your subroutine name. So we have 2 in this program, in this lab. So we have the molt and the div, okay. And then we're going to have a halt. And then after that, we're going to define the subroutine. So you would use a label, just like what you use with loop. So we would have a label called molt and a label called div. And then here they put some comments for you. So we need to begin by saving your register that will be overwritten, because if your data gets updated, you want to save and then later restore, okay? So when you begin your multiplication, you need to think about your data needs to be saved to a register. And then you would implement the algorithm. How are you going to represent multiplication? Then after that, you are going to restore save register. Then a certain register is going to have your product, right? And then we're going to return from that register. So, and then because after it operates the function definition or the subroutine definition here, remember that it needs to pick up, and it needs to, because we have a second function call or a subroutine call, then it's going to load the address for the next one. And that's where it's going to increment, and it's going to start executing the next function or the next subroutine. So in the second function call here, or the subroutine call, it's going to jump to here. And then just like the other one, we have to save register, we implement the division algorithm, we restore register, we put that onto a register, return from that register, and then, we end the program. Okay. So when you approach these things, you really have to think about, how do I set up my subroutine? And so that the calls get handled at the beginning, and then you just simply doing the definition. So we will also have subroutine and things for stack later. Okay, in the later lab, you are going to write stack, because in this class, we're also going to handle data structure as well. Okay, any question? All right, so let's talk about multiplication, right? And this is fairly an easy program. It seems complex at the beginning, but it's not. Okay, so you're asked to compute the product of x, y. That means that we're going to take x, we're going to multiply it by y, and it could be any integer value. So x times y represents x plus x y times. Okay, so if I have x is 2 and y is 3, all that is 2 plus 2 plus 2 plus 2, right? 3 times, because I would do 2 plus 2 plus 2. That will be 6. Okay. So when you think about multiplication at the assembly level, because the computer only adds, you would think about how you can represent multiplication and division as addition. Any question? All right, so with that, we're going to look at listing 5.4. So they give you the pseudocode here, and that's going to help you out with the multiplication algorithm. Okay. And keep in mind that X could be negative or positive value, and so is Y. Okay. However, when you deal with division, right, you would have a logical error if Y is 0. Because if you take X divided by Y, Y cannot be a 0. Okay. So we have to think about how we would be able to control that as well. So first, we're going to look at the pseudocode for multiplying X. Okay. And we want to represent XY. So X could be a negative value. So we need to handle that first. So we have to say, okay, well, if X is less than 0, then X needs to be represent sine X. Okay, so we have to represent the sine X. And so here we would have X is equal to negative X, right? In the case that it's less than 0. And so we would say that the sine needs to be, so your X is going to be sine X. Then Y, if Y is less than 0, then we also have to represent Y is sine Y. Okay. But for the division, we have to implement the condition in that Y cannot be a 0 because you cannot divide anything by 0. That will create a logical error. So we would say while Y is not 0, find the product, right? So your product is going to be X times Y. Okay. And then Y is, and here we're going to represent Y minus 1 because, again, that's a loop. So we need to count. If sine is less than 0, then your product is going to be negative. So if I take a negative X, I multiply it by a positive Y, I would have a negative value. And we want to represent that, right? Because if you don't do that, then you're only going to handle the positive value, which is not the realistic approach. Okay. So we need to make sure that it is sign adjusted in the product in the case that your X is negative or your Y is negative. Okay, and in the case that if they're both negative, we got to represent that as positive, because if I have negative X times negative Y, I would have a positive product. All right. Any questions regarding multiplication? And we're going to come back to this when we go through the code again, piece by piece. So, okay, let's talk about division. So, we want to find the result for X divided by Y. Okay, so for the integer division, we would have X divided by Y, and we would have mod X mod Y. And we want to satisfy this formula. X is equal to X divided by Y times Y plus X mod Y. Okay. So in the division, if you think about like even long division, if you take X divided by Y, you would have a quotient. Okay. And depending on the value, with some value, you have a quotient and a remainder. And you need to handle that remainder because it just doesn't disappear, right? It's still going to be there. So what we need to do is we need to think about how we would represent the remainder with the X mod Y. So in the example here, if you take X is 41 as a decimal value and you divide it by Y, right? So if you take 41 divided by Y, you would have a quotient with the remainder. If you punch that into a calculator, you would have what we call a decimal point value or float. right? So now if you break that down into how you would see 41 from the 7, right? So 7, we can take 7 multiplied by 5, and that's going to give us 35. So at this point here, right, the highlighted area, that will be 35. And the difference between 35 and 41 is a 6, okay? So you have to think about, okay, so how can I represent this? So if you do take 41 divided by 7, right, if you punch that as a modulus value, you have to think about, oh, am I going to have a remainder? Okay, so this kind of show you the breakdown on how you would approach the getting a result with a quotient and a remainder. Okay, so now in this section, it talks about subroutine diff. So when we set up the diff subroutine, we have to think about a quotient and a remainder. So we need to pass x into the parameter, right? And that's going to come through register 0, just like what we've seen in the previous section. And then y is going to be register 1. And you want to track your register. We want to use the same register so that way we don't confuse ourselves even when we're going from multiplication to division. Because when you load the x and the y at the beginning, you can copy it to a register, but you don't change all of that, right? So you can reuse those the label or the variable to the register. So since we load it to 0 and 1, we're going to continue to use that there. Okay. And so here we can simply implement the division and the modulus by defining, right, on x and y. So if y needs to be greater than 0, it cannot be equal to 0 or less than, or it can be less than 0, but here we need to specify the condition, define only when x is 0 and y is greater than 0. So for the subroutine, when it should check the condition that's satisfied, it should return with register 0 as, or register 2 as 0. So in the case where if I have x is 0, if 0 divided by any number, the result is 0. Okay. Similarly, when we think about multiplication, if you're taking a 0 and you multiply it by any number, you need to have an output of 0, right? So we would return a 0 in the case that x is 0 and y could be any number, and that could be positive value, right? So if I have y is 1 multiplied by 0, which is x, then I would have an output of 0. And that's what it's saying there. Okay. Now, if they are satisfied, then your register 2 holds 1 to indicate that the result is valid. Okay. Now, in the overflow condition, it cannot be checked at this time. So we're not really handling the overflow. So here is a table. It shows you that this is your register 0, which is x, right? And when you take x divided by y, we would output a 0 if it is invalid. If you have x mod y, it would also output 0 if it is invalid. Now, if register 2 holds the 1, then it is valid. So if we return 1, then we have a valid value. Okay. So with that, we would look at listing 5.5. So you would initialize your quotient at 0. Okay, so that means that we just clear the register, right? And then your remainder, we would initialize that at 0. And then valid, we initialize valid. Then we would apply the condition for x and y when it's positive and negative. So if X is a negative value when it's less than 0, or Y is equal to 0 or negative value, then it's going to exit. Okay. And so for valid, then we want to initialize valid at 1. So we want to add the 1 to whatever that register would be, right? Which is register 2. Now your temp is going to be X, so it's going to hold quantity left, so we can copy that to another register. While temp is greater than Y, okay, it's going to take the temp location, subtract Y, because division is subtraction multiple times. So think about the long division. When you're taking X divided by Y, right, you have a quotient, and then you operate the subtraction from, you know, the bottom side, and then you have what's left over, and you continue to do that. So you're always going to have a quotient, and at some point you might have a remainder. So you need to have a location where you're going to hold your quotient and a location where you're going to hold your remainder in a division subroutine. Okay. So here we are going to implement a while loop, and your temp location is going to be greater than or equal to Y. So it's going to hold the value for your quotient and your remainder. Okay, any question with that? So I think when you're looking at the code, it might be confusing until you look at these, right? So when you write your project, you want to write out your pseudocode, and pieces of your pseudocode, you want to go and think about how you would tie your subroutine into the pseudocode, or write your subroutine, and then how you would implement your loops. And so therefore you can branch and set up your conditions, and so it will flow out accordingly. Otherwise, you're going to have missing parts. So in your task, we're just going to create one program today. We're going to handle multiplication and division. I already explained everything with the listing, so you can test your program with different values. You don't have to use it with this. But at one point, we want to see if Y is 0, if that handles properly. And remember, you have to set value in the simulator and go to the location to look at your output. It will not output on console, so do not look at console for this particular lab. Okay, so you need to go to the hex 3100 and up to look at your input and your output. Okay, I need you to answer these questions. And so what are some of the key points that you learned from this lab? Because this lab is really important for, you know, a lot of the additional lab. Not only that, it drives home some of the understanding on what the compiler does with your function and function call in other languages, okay, like C. Then if you have any kind of challenges in this lab, you need to identify that, not only for me to see what I need to help you with, but also to think about what you need to improve upon as far as going back, review, and think about how you would be able to solve the problem or understanding a certain process in the program. Okay. And then C, how can you apply subroutines in your future exercises and project? Okay. And remember that subroutine or functions are designed to be reused. So we want to have a section of our code that we can refer to in case we need to. And we don't want to write a really lengthy program to do the same thing repeatedly. We want to be able to use the function for that. Okay, any questions? All right, so as you look at the screenshot that I had posted, okay, let's go through line by line on this. And so if you have any questions, please ask. So the original program was for lab 7, but since we have the holiday, we didn't have a lab. So now we're going to do that in week 8. But I relabeled the lab so it doesn't confuse you. Okay. Okay. So we are going to use subroutine for multiplication division, and the division subroutine is going to handle mod. I have a chat. Okay, yep, not a problem. See you next time. So since we're doing x times y and x divided by y, right, after your origination address, which always starts at hex 3000 for us, then you are going to load register 1 with x. So we're going to do an LDI R1X. Then next, we're going to load the Y to register 2. Can you do register 0? Yeah, you can. 0 and 1, just make sure you track them. Right away after your load, you're going to do a function call or a subroutine call or jump to subroutine. So we're going to do a jump to subroutine molt. So at this point, after it loads the label, it's going to go to here. Okay. And then it's going to come back up, right? And then it's going to store, and then it's going to do the next one. So think of this part as your main in C, okay? Where you declare a variable, and then you would do a function call and so on. Okay. Then for the next line, so we're always going to put that first. So when you look at the program with a subroutine, you already know that when you see a JSR, that's a function, that's a subroutine. Okay. Then we are going to store from a certain register, right? Which is going to be our product, our f of n or xy. So we're going to store it from the register 3 to xy. Okay. So your product is in register 3. And we're going to call the division function or jump to subroutine div. And then that's going to be in register 5 for the quotient and another register for the remainder. Remember that we only have so many general registers, so we need to make sure that we are reusing some of the register, and we need to save and restore, right? As your data also gets updated. So we are going to have a register 5 that's going to be for quotient, and R3 is going to be for your remainder. And we're going to hold there.
Professor.
Yes.
Why do you have it register 5 instead of register 4? Do we use it already, or?
No, it's not necessarily that we use it already. There's a use for register 4 down here.
Okay.
I just choose to use register 5 because it's a choice. It's a preference. So register 5, we have it with the save register 2. Also, you know, that's really a choice. So you can use register 4 as long as, you know, that register doesn't get updated with other things down the line. So, okay. Other questions? All right, so let's talk about your definition for your subroutine molt now. Okay, so we talked about how this could be like your main in your C, C++. Then your molt. So here we would have a label molt, and that would represent your subroutine definition here. And you can tab it so it's a little cleaner, right? I see a chat. Okay. You too. Thank you. So the first thing I need to do is I need to store register, right? We know that we will get updated in that we have to handle multiplication and division. So we want to, and also it would update the value in the multiplication. So we would have a store R5, and we would say save reg 5. That's going to save register 5, and that ties to a label. We're going to do a store R6, save reg 6. Okay. Now I'm going to take Y, which is in R2, register 2, which is Y, and I'm going to copy it to register 4. The reason why I'm doing that is because I'm using Y again later on for division, and I don't want to change it. So I need to copy it to another register, right? Because it's x times y, and x divided by y. So we're going to copy y to register 4. And then we are going to invert. So this is the 1's complement, and then it's the 2nd complement, or the 2's complement here. So here at this point, your R4 is going to hold negative y. Okay. Why am I doing that, right? You just say, why do you have to do a negative y there? Okay, let's go back. See this? We have to treat it where it could be a negative value, right? Because y can be positive or negative. So we have to apply this condition. If y is less than 0, we would sign the y. So here is where we sign the y. Okay? That's what we're doing here. Okay? And with that, we would branch. So it's going to look at the value from register 4, or the destination register from the previous line, and it's going to branch. So here we want to branch positive to positive loop. So for the negative value that comes, that becomes positive, it's going to need a negative counter instead. Okay. What do I mean by that? Right? So here, what they're saying here is that we need to have the adjustment in the product based on how you sign your input x and y. So if I have a negative y times a positive x, I have a negative product. If vice versa, and then if I have both negative, I would have a positive value. Okay, so I have to handle these conditions first in my function or my subroutine. So in the next part, I'm going to set up a loop. Okay, and this loop is going to represent the multiplication, right? Because if I multiply, I'm just adding it repeatedly. Okay. So we are storing register 5, right? And we're storing register 6. Okay. So here is where we're going to use those register. Your register 6 is the destination register. We're going to add register 4 and register 5 together. Your register 4 is what? Your y representation, right? Remember how we copied that over. And your register 5 is what we're going to use for your output at one point. Okay, so here it tells you that it's going to check if n is greater than 0, if yes, quit. Okay, so where is it going to check? From register 6. So if it's 0 and positive, it's going to go to quit 1. So what am I doing now, right? Remember that when we, let me see if I have. We have this section here, right? So if x is less than 0, y is less than or equal to 0, this is because y is less than or equal to 0, we're going to exit. Okay, so now what we need to do is we need to say if it's 0 or positive, we're going to go to quit 1. Okay, because now we're handling the y, which is an R0, R4. And then we're going to increment the counter. So we're going to do a +1. After that, we are going to have, it's going to multiply until it hits 0. So when we're multiplying, we're just adding it multiple times. And so as we do that, we can count it down You can think of it that way, where the counter goes down every time. Like if you think about the for loop, it's going to go all the way to the max, right? The maximum value that you set for your for loop. But when you are using assembly, you can think about when it's going to count down every time it loops. Like if I do multiply by 6, I would do 6, 5, 4, 3, 2, 1 until it hits 0, then it's going to stop. So it's going to come back to the loop every single time until it's done multiplying, which is where it hits the 0. Okay. And earlier we had it branched to quit 1, and quit 1 we simply going to return. Okay, because when we multiply, the whole point in writing a method, a function, or a subroutine is to return from it. Okay, so it's going to keep looping until it reaches the maximum value, or when we think in assembly 0, right? And then it's going to be back to calling the program. So it's after it returns, then it's going to go to the next load, and then, or the next part here, and then it's going to go to the next subroutine and so on. Okay, so at return, it's going to load the register 7 with the address, and that's how it's going to get the value. So earlier we have a positive loop. We have to stick it in there somewhere, right? So here is our label, pos loop. We are going to clear register 4, because earlier we used register 4 to temporarily hold Y, and then we inverted it. So now we're going to clear register 4. And then for loop 2, it's going to be the same as the other loop, right? But we would have a quit 2 label. So that means that it's going to take Y that was, I'm sorry, when I said clear register 4, I that was wrong. So that take 0, add it with Y, so Y plus 0, and then put it back into register 4. So now we are going to take that, and then we're going to add it with register 5 and put it in register 6, just like what we did previously. Okay. Now in this one, we're only going to branch it when it's 0. We're going to send it to quit 2. Okay. So when you come back to the listing, what we're really doing, oh, right here. Okay. So earlier we already handled this part. So now we're going to handle this part right here. Okay. So we would send it to quit 2, and then for R5, if you recall earlier, we have it saved to the register, and in the last one, we would represent that by having that as N. So we're going to take 1, we're going to add it to R5 and put it back on R5. If it is negative, then we are going to, so for R3, we're going to take that and add X to R3. So here, your R3 is going to hold, let me double check, multiplying the counter R1. So here is where we have it multiplied. So it's just the same thing. So that's going to represent a multiplication of a negative value. If it has a negative value in Y, then we would represent that in the loop. So you're still going to, when you have X times negative Y or negative X times Y, it's still going to multiply that value, but at the end you have to sign the value. Okay, it's still going to represent the same thing. So if I take -2 times 3, I still have a 6, but I just signed the 6 to represent the -6. Okay, so that's what we're doing, is we're still going to have the same thing as the positive, but what happens is we have to sign the value to represent that either X or Y is a negative value. Okay, so with this, Okay, what we want to do is we want to keep it like what we did in the previous loop, where we will multiply the counter and we're going to keep looping until it hits 0, right? Now, the only difference between the previous loop and this loop is we're going to branch to 0, where that would be when it hits 0, then it would go to quick 2, which is where we are going to do the 2 complement. So that's how we can represent that the value, right, is a negative value. Whereas the previous one, when we do 0 and positive, we want to keep checking that if n is greater than 0. And at this one, we're going to check if n is less than 0. Okay. Any question? All right. So in quick 2, we talked about inverting it here. So that's going to give, we do the 2 complement for register 3. So in the negative after they multiply. So we represent the negative value of the product, right, in register 3 by inverting it, because you still have the same value. Now you just have to sign it. Okay. Any question? Okay. So since we save register up here, we need to load it down here. So you restore R5 and R6. Then you do an RET, so you return. So at that point, after it hits this right here, it's going to go back and it's going to pick up here. Okay. And then go to the next. It's going to jump to the division section after that. Okay. So when you're using save register, we don't need to tie it to an actual address. You can just fill it with the hex 0 and hex 0 for both of these labels. Okay. Any question regarding the multiplication? Okay, so now because it's going to jump to the division subroutine, we're going to define that here. Okay. Recall that earlier we load R2 as Y, so we are going to initialize Y is 0. We want to check that because you cannot divide by 0. It's a logical error. So at this point, you simply add it with the 0. So it's going to check R2 and we want to branch it to 0. And if it is 0, we're going to make it quit, exit. Okay, return. So check the condition for Y as 0. And if it's not, then it's going to continue to the next part. We are going to take Y and we're going to add it with 0 and we're going to put it on R6. So we're going to take Y and put it on R6. That's same as copy. So we copy it to R6. Then we are going to clear R5. Then we are going to we're going to copy X from R1 and put it on R3. Then again, we are going to take Y and put it on R4. So why am I using 2 register for Y, you should ask, right? Because I need to handle the division and the mod together. Okay, so that's why I'm getting those register ready so that way I can do the division and the mod. Okay, so after I have Y in R4, I'm going to operate the 1's complement and the 2's complement to make it inverted. So at this point, R4 is going to hold, is holding negative Y. So we can subtract, right? Because division is really subtraction multiple times. So now what we're going to do is we are going to subtract. So my R0 is going to hold X, subtract Y. Okay. And then we are going to branch for negative. So it's going to check R0 for the result. If it is negative, it's going to go to quit 2, which is up here. And I'm reusing the section. Can you have another quit section for the division? Sure, but if this is why I wanted to stick with something that's the same for both. So we can reuse some of the section. Okay. So we're going to send it back to quit 2. Then in loop 3, we're going to start with the counter. We're going to increment 1. So take 1, add it with register 5, and recall that we clear register 5 up here. Okay. And so now we increment. So that's going to be a +1. Remember, when you look at the diagram earlier, we need to get the PC, take the JSR address +1. Then we are going to subtract XY again. Okay. So now at this point, R3 is going to hold X minus Y. So I'll put that here. And it's going to look at the result in register 3 to verify. So if that value is positive, it's going to go to loop 3. If it's 0, it's going to go to quit 3. Question? No? Okay. And then if it's negative, it's going to take the result, it's going to plus the Y. And then if it's negative, right, we are going to take that and we're going to subtract the counter. So we are going to take R5, which originally we had 1 there, right? So if it's negative, it's going to add the counter +1. Then we are going to keep branching to quit 3. So we do an unconditional branch and we're going to go to quit 3, which is return. Okay. Then you're going to be back to calling the program. So after that, we simply just do a data section. We are going to fill X, we're going to fill Y, we're going to fill the X times Y, the quotient, the remainder, and the end. Okay. So efficient wise, we are able to use a couple of the label section for both because they share the same thing. And that's why there's certain register that I dedicate to, so that way I don't have, so if I don't do that, I'm going to end up having to write different section, different label section for the division separately. So we want to stick with how we're tracking the register. If it's sharing the same condition, then we can apply the same condition. So when you look at the condition, right, the multiplication condition, that will be applying the same for the division condition. So as X could be negative, X could be positive, Y could be negative, Y could be positive. The only thing that we also wanted to treat is for the division is that we want to make sure that we check for Y cannot be 0. And we did that in the program right here. And that's a little different. So, you know, and then everything else, right? Everything else we define in the subroutine individually. Now, after writing this program, you can multiply anything, right? You can think about, so we have 2 input at this point, X and Y, but you know, so I had a question from YouTube. The individual asked me about how do I do X to the X power or treat it X an exponent? And simply, you know, my answer would be JSR multiplication, and then how you can use that and apply that as an exponent value, because ultimately it's still multiplication. Okay. Okay, so after this, you would save the program, right, as an ASN, and then you would assemble it. So let me go and open up my simulator and load it. So after you assemble it, you can run it. Okay, so then we can, before we run, we want to set the value. Okay, so we are going to set X. So your hex 3100, right? We can do a hex 2, apply, and then let me double check. It's 3101, I believe. Yep. So 3101 for Y. And then we can make that a 3. And then we run. After we run, we jump 2. So we have, oh, here's your X, which is 2. Here's your Y. I have a hex 6. That's correct. Okay. So if I take 2 divided by 3, I have a 0 as a quotient, right? Now you can test it with another number. Let's test it with another number. Let me reinitialize the machine, reload the program. Let's do a large number for X to see if the division works. Okay. So we will go to hex 3100, and then let's do 8 for X. And then I wanted to use a different number, not an even number for Y. So let's do 3 for Y to see if it handles the mod. And so after that, I can go ahead and run, then jump 2. So X is 8, Y is 3. 8 times 3, I have hex 18. Okay, remember that this is hexadecimal, not your decimal value. Okay, if you want to check, you can also use your calculator. You can check. And then for my division, I would do 8 divided by 3. I have a 2 as the quotient and a 2 as remainder, so it checks out. Now remember that we're not controlling overflow. So in the lab, I wrote that you can test it with the larger value. You will find that we are gonna hit a limit in the case that, you know, because our word size, we can only handle a certain bit equivalent values. Like for example, our immediate value needs to be fitting in the 5 bits. So in this one, we didn't make additional space for anything that would be large in values. Okay, but it did handle my quotient and my remainder there. Any question? So I like for you to test it and see, and also use like negative and positive values to see if, you know, if the program is accurate. And then you can think about how you can also improve the program. Any questions? So with this lab, you see how we can save and restore register. We use jump to subroutine. We return from our subroutine. We implement the conditions for our input. Okay. And we're able to use multiple subroutine, or at least 2 in the program. Okay. And as you proceed in this class, our program will get a little bit more complex, but this is simple. So in the next lab, we are gonna multiply, but we are gonna shift when we're gonna do the bit shift instead of doing it like this way. So you would see how you can approach it a different way. Any question? Okay, so going back to Mr. Tucker's question earlier, why I was not using R4, because I had used R4 for my loop to copy things over, so that way I don't change my Y and or my X at some point with 3 and 5. So I was using 2 and 4 for my Y, and then 3 and 5 for my X, and then 6 was just, to be used for like checking and things like that. And then eventually I store that out and load. Okay. So save and restore. All right. Any question regarding the lab? Okay. So one thing that I want to remind you, there is a homework assignment that's due at the end of the week. Don't forget to do that. It's going to help you prepare for your quiz. Okay. When we come back from spring break, no school next week, but after you come back from spring break, you will have a quiz. There will be a quiz game or a quiz review game happening in week 9 after we return. In about that week or the following week, I will talk about the project. I will post, and I'm going to try a different approach this semester. I'm going to post a discussion thread where you can communicate with your classmate through there to be able to identify your groups, because I found that it's challenging to really set up groups virtually for students and, encourage you to be in a group. I will also embed the thread with my Google document, so where you can add your name onto a list to, so that way you can set up your team. And I will leave it up to you on how you set up your schedule to communicate with your team. But keep in mind that the biggest challenge in working in team for the time that I teach this class, when I even face-to-face, when I make them do team projects for programming, is to find the time that will match other people's schedule to work on your project. So, trying to coordinate and things, and remember that, you work with other people. So think about how you would compromise and be able to work a little bit, and just to achieve understanding. I know most of you can probably do the project by yourself, but that's not how it operates. In the real world, you will have development team, and you will have people that you work with remotely. So we have to understand how to adjust our schedule and make it work. And so you would have a solid, I want to say 4 to 5 weeks to work on your project. You won't have all the components built until we hit some of the exercises where we would, work on stack and things. So as you proceed, we're going to have a few more labs. And as you do the lab, you would understand how to approach your project, because I write the requirement based on what I cover in the class. So leaving this class, you should have a knowledge of solid LC-3 or assembly programming, and be able to solve at least on the simple problems. So things like bubble sort, and, basic encryption and stuff like that at assembly level. Okay, so that's what's expected in this class. For the project is you can pick the case that you want to use for your project. Any question? Okay, so in 9, we are going to cover stack. And then we are going to look at data structure and how to use data structure in LC-3. Then in 11, we are going to do pointers and arrays. So you are going to work with larger data sets there. And then in 12, we are going to do recursion. So we're going to look at recursive functions. I'm only going to do, I think, lab up to about week 10. Okay, so the lab time that you're going to have after week 10 should be dedicated to teamwork as you are scheduled for class. I will do final review at some point in the lecture, as we are going to cover only so many units from the book, because those are the chapters that we cover. And so I will let you know in the regular lecture time, I will cover the final review where we looked at, the entire semester content. And, you will have some part of your final is going to be concept based, and some part we're going to touch on LC-3 and some of the things that you've learned in LC-3. Okay. All right. Any question? Okay. So finish a little early today. If you don't have any question, you can put your name into the chat. Make sure that you turn in your work by Sunday. And I am already I finished grading your unit 6. So I'm working on the lab 7 and finishing lab 7. So I should be caught up by tonight in your class, unless you just turn in something like a few minutes ago. Okay, have a wonderful spring break. I hope to see you back when we return, and be safe and have fun and try to relax and have a good weekend as well. I'm going to stop recording.
Goodbye, Professor.